Hello, everyone. If you've just joined us, we're just waiting a few minutes. Hello again, welcome. I know it is 1 o'clock by my clock right now, but I'm just going to wait 1 or 2 minutes because I see that the attendee count is still rising. Okay, I will get started. Well, yeah, I think it's time to get started. One second, please. Okay, welcome to the Center for Quantum Networks Thrust for Quantum Society lecture. I'm so pleased to have Laura DeNardis and Sandra Brahman with us. They are both incredibly prolific and well-respected scholars in the field of internet governance. And they are both fellows with us here in Thrust 4 in the Center for Quantum Networks. So I'm Jane Bambauer. I am the Deputy Director for Societal Impact for the Center for Quantum Networks and also a law professor at the University of Arizona. But my role here is going to be minimal today. Laura DeNardis is an internet governance scholar and professor in the School of Communication at American University, where she also directs the Internet Governance Lab and has written several very important articles and books on the topic. Globally respected and renowned scholar. Dr. Sandra Brahman is the John Paul Abbott Professor of Liberal Arts in the Department of Communication at Texas A&M. And each of them is going to talk for about 25 minutes. This event was centered around Laura's work as a CQN fellow. She has a draft related to the topic that she's going to talk about today. And then Sandra will follow up with some much more detailed comments than a typical commentator is normally asked to do. So thank you very much, Sandra, for that. I will be monitoring the Q&A board. So please feel free at any time during their talks to log questions there. And we will get to as many as we can during the last 10 minutes or so of today's presentation. So, without further delay, Laura, do you want to take it over?
Thank you very much, Jane, and hi everyone. It's really great to be with you to discuss quantum internet protocols, research supported by the Center for Quantum Networks. I'm especially delighted that we have people in attendance today from both the quantum world and the internet design world. So I thought I would start with a personal story that involves both of those worlds. 16 years ago, while I was still at the Yale Information Society Project, we organized an Access to Knowledge conference in Geneva. And as fate would have it, I was on the stage in Geneva giving a talk on the internet protocol at the exact moment when CERN's Large Hadron Collider was fired up for the first time in the miles beneath the Swiss and France border. Now, I was far more interested in that than my talk, and my family asked me, would I be swallowed up by a black hole? Of course, what I wanted to know is, what, if anything, does this mean for the internet? The first time I had that kind of a nagging question about the internet's fate was when I was even years before that, when I was a Cornell engineering graduate student, when the Morris worm, unleashed by a fellow graduate student, was the first attack to disrupt the internet. The web wasn't born. I think Zuckerberg was probably a toddler at that point, but the incident ushered in sudden media attention, sudden policy attention to the internet. It resulted in a prosecution under the brand new Computer Fraud and Abuse Act and the formation of the very first Computer Emergency Response Team, or CERT. And it ushered in my own path into internet architecture and governance. I wanted to say that since then, both in my in private industry and also in higher education, the basic thesis of all of my work has been, if you can sum it up in one sentence, that arrangements of technology are also arrangements of power. And I've specialized primarily in the politics of emerging technologies, first on the next generation internet, on cybersecurity innovations. I have a book on IoT governance, for example, and now I hope that quantum networks will be a terrain of my interrogation in this area. Now, even standards within that broad field of the politics of technology, even standards, whether they're quantum or not, have societal impacts. And I know that Sandra will talk about this, so I won't belabor the point, but some of you are probably familiar that digital accessibility standards empower those with hearing or sight issues. Standards can shape privacy and speech rights, access rights. The degree of openness and intellectual property rights restrictions affect economic competition and the right to innovate. And highly relevant to this topic, encryption standards are especially political, with things like battles over key strength or even export restrictions, always mediating tensions between things like law enforcement and intelligence gathering and privacy and the stability of the economy. So I'm very interested in the question, what will quantum technology advancements mean for society and for the internet itself? No, a disclosure, just in case anyone doesn't know, I come from the internet world, the world of internet architecture and governance. I'm happy to see some of my colleagues on this webinar today. So I don't come from the quantum physics world, although I've always loved physics. And so I've been very interested in learning a lot about the difference between quantum and digital, and interested to know what a diverse area it is, quantum information science, and how different qubits are from bits, the basis of all digital systems. So there's quantum sensing and metrology. You could describe that as the detection and measurement of physical properties such as temperature. It's highly relevant to the Internet of Things. Of course, there's quantum computing and there's quantum communications, the application of quantum principles to the transmission and security of information. I've been really enjoying looking through patent filings in this area. The possible applications are stunning for genomic medicine, for molecular simulation. It's such a diverse area for battery life, for weather prediction, and really anything that requires computational power. But this realm is so different from the digital world, which is based largely on discrete units and predictable calculations. I mean, there are probabilistic calculations in making the digital world work, but it's primarily discrete and predictable. So any information from text to audio, video, images, any information can be represented by combinations of zeros and ones, known as bits. That just stands for binary digit, and routed over a network. That is highly discrete. Now, as my new colleague and associate in the center, Michael Raymer, explains in his work, quantum physics, he explains a lot, but one thing that I picked up on is just how this world behaves probabilistically. And it does so in a way that clashes with our everyday perceptions of the world. I know it certainly clashes with my perceptions of the world. At an atomic level of photons and electrons, quantum bits or qubits can observationally take on a value of either 0 and 1 at a given time because of the quantum mechanics property of superposition. And I've also been very interested to learn about the feature of entanglement, suggesting that unlike independent discrete bits, qubits can have a correlation or connection to each other in any moment, even over a distance. So this is complicated, and it sounds like the world of Star Trek to people who are not quantum physics majors or scholars. But a point that I would like to make is that internet architecture is also complex. And it is not one thing. It is not literally a cloud. It is not a series of pipes. It is far more than repeaters. And so it is with the protocols of that system as well. So the internet is an entire ecosystem of technologies whose interoperability is made possible by standards. In the same way that Dr. Brayman and I can communicate with each other using common formats, common ways to greet each other. We can send each other a letter in the mail using common addressing formats, and we use common language and grammar. Just like that, digital systems can communicate with each other because of these common protocols and languages. So they have to answer a lot of questions. How do you translate something like a human readable domain name into a binary number? How do you encode? How do you do the encoding of any information into zeros and ones? How do you compress information? How do you do error detection and correction? How do you address something and route it over a diverse network so that it can reach its destination? How do you authenticate not only people, but resources and objects that are connected to the network? How do you protect information in transit and at rest? And perhaps even most importantly and relevant to this discussion, how do you do the handoff between networks, which we call autonomous systems, at the boundaries of those networks? How do you do that handoff? So there's not one standard that makes the internet work. As I read through the various physics articles about this, I noticed that HTTPS is mentioned a lot, but I thought I would just list in no particular order some of the other standards that make this happen. And these are just a few of them. And there's also an entire system of standards bodies, which is also an acronym stew. The IETF is the Internet Engineering Task Force that sets many of the core internet standards. But there's also the World Wide Web Consortium, the IEEE, the ITU. So national bodies, international standards bodies. This is such a capacious area, and it involves so many organizations of so many different stripes. So I want to say that the core, Sandra, no doubt we'll talk about this, but the core internet standards, they are documented in the RFCs, which is the request for comments series. It's an archive that has documented internet standards and related information since, I believe, 1969. And I just want to have a fun slide here noting that internet engineers are definitely not without humor. And if you see one on April 1st, it's likely to be an April Fool's joke, such as one of my favorite, the quantum bug. Poking fun at quantum networks. I think I have on the slide a quote from that, discussing faster than light communication, where packets arrive before they are sent, and suggesting that, quote, we have to accept the cold facts. Time travel will never work, or it would already have been used. So that's fun, but the serious side of this humor is that quantum technology is not only an issue of physics, but it's indeed an issue of information science, of cybersecurity, and of the possible future of communication networks. And some of the societal impacts at the quantum internet boundary are well understood and well articulated. But I want to move one forward today by suggesting the impact of the quantum computing threat to public key cryptography as an area that's about far more than just privacy. So it's rare. I think anyone in this the internet architecture world would agree with this, that technical standards communities are rarely in complete unanimous agreement. But if you look and troll through the archives and their mailing lists and what they're working on in this area, they concur that quantum computing has serious cybersecurity implications. I selected just a few quotes to share on this slide, and you can read them yourselves, but I want to pay special attention to the quote from ETSI, the European Telecommunication Standards Institute, because that one captures the point that almost all public key cryptography in fielded security products and protocols today use some of those ciphers. So that's a crucial concern that is being discussed right now. The crucial background issue is that the internet runs on public key cryptography. So I've heard many people talk about this, but they haven't talked about the layers and layers that are affected by this. So if there's only one or two takeaways or one takeaway from my comments today, it's this, that this is not merely an issue of threatening individual privacy and decoding information captured in transit or at rest. Many of these vulnerable approaches, such as DH or ECDH, they underlie key operational functions of internet infrastructure. I thought I would list a few here, and I think it's still, a lot of this is still being discussed in terms of the extent of impact in these areas. But one example is Internet Key Exchange Protocol that provides a basis of support for IPsec, which is a protocol that underlies many different critical functions, from access control to authenticating data sources to data integrity. So that's one area. Another is the question of how do you know if a website is authentic when you access it, such as bankofamerica.com or a press release on whitehouse.gov. It's because of the trust protocols using public key cryptography and HTTPS and the connection between that and transport layer security, TLS, and then how that connects to the certificate authorities, which are actual institutions that certify that trust function and that encode that trust in browsers. So that's another area. And another critical application area that uses public key cryptography is domain name system security extensions. And that has to do with authenticating the queries that are resolved online between domain names and IP addresses. And it's very difficult to imagine the internet functioning without that. So it's used for a number of things in the core operation of the internet. So this is all, it's at the content layer, but also at the logical layer and at the system of trust and authentication that keeps the internet running. I want to mention also that public key cryptography is used to validate access to Bitcoin and used to validate or maybe authenticate users is a better way to say it. In virtual private networks. So I would love to spend just a day, a full day in a room discussing this and how some of the quantum applications that I'm learning about as part of this network, how that plans to connect to the different protocols there. So the critical point is that the quantum threat is about far more than just keeping data private in transit or at rest. It's about the very core basis of how the internet functions. So not surprisingly, the security attention is emerging at all levels of, I use the term quantum internet entanglements. It helped me to understand or deconstruct the main categories of activity at this intersection. So in reverse order on this slide, one area of exploration is what you could call a full quantum internet that provides fundamentally new technology by enabling quantum communication between any two points on Earth. So that's very futuristic looking. Another approach is the overlay of quantum on top of classical approaches. So in this area, there's a tremendous amount of investment and attention, and a lot of it has been directed at quantum key distribution. So using principles from quantum to generate and secure and distribute symmetric encryption keys between 2 points over a dedicated optical link, for example. And as an aside, a great deal has to be worked out in that area. There are many questions, such as how this parallel system would deal with on-the-ground realities in a network, such as addressing and routing and the handoff between two networks. So that's a really interesting area and one that's very complicated. And then yet another approach is what could be called a quantum safe internet. It's also called quantum resistant, to shore up existing systems, to defend against quantum computing brute force attacks. So this is the post-quantum cryptography area. There are a lot of acronyms around this area. Many on this call are familiar, of course, with NIST's ongoing post-quantum standardization processes and soliciting worldwide proposals to try to standardize and shore up quantum resistant public key cryptographic algorithms. That's a mouthful, sorry about that. So where are all of these conversations happening relevant to the underlying standards? This is just not a complete slide, but I wanted to give a sense and put some of the standards organizations here. It's been really interesting over time to see one indicator of evolving technologies. It's whether standards organizations have established future-looking working groups. And that is certainly the case with quantum networking. Some efforts are in national standards development organizations. Some are in international bodies. Some are in private consortia. Some are in the dominant internet engineering communities with multi-stakeholder engagement, such as the IETF. But it's really a very, very diverse area. And I thought I would share a few observations about the state of this, and then discuss some lessons from internet standards, possibly for this area. So these are nascent. These are future looking. Most are less than 5 years old. They seem to be forming a landscape of multiple competing standards organizations doing work in some cases in similar areas. I've noticed that there's not consistent terminology among some of the efforts, the various efforts, and engineering challenges abound to move theory into practice, to go from experiment into the real world, such as how to deal with transmission loss, gate errors, memory decay, integration with routing and addressing, and integration with the core standards, some of which I've already mentioned. So that is incredibly interesting. That's why this is what I'm very interested in, to look at the efforts and the coordination between the different groups. I want to conclude by suggesting some internet standards insights for quantum networks. And this applies whether it's a quantum internet, it applies whether it's a quantum enhanced internet, and it applies for a quantum resistant internet. The first is the need for interoperability with the existing architecture of the internet. And I know that many people disagree with that, but in my opinion, I don't see how this can progress without being part of the classical internet. So this is in large part because of the conservative momentum, as a historian of technology, Thomas Hughes describes it, the conservative momentum of entrenched standards, the large installed base, the expertise, the expense of upgrading, there are economic, there are social externality issues. So achieving this necessary interoperability, it requires collaboration as things move from experiment and beyond between emerging innovators and the expert communities that are already involved in the design and coordination of the internet's core architecture. The second insight is to focus on infrastructure, not just content and applications. The public policy questions are just as much about infrastructure as they are about the information and the content that is exchanged over a network. So too should quantum security not just be about privacy between people or of information, but also how to protect the core infrastructure of the internet upon which the economy and society now depend. The third insight is to avoid fragmentation and an anti-competitive future by trying to harmonize and trying to retain the norm of open standards that have created the innovation that is the internet. So internet standards generally have a history of openness. This is openness in participation, openness in implementation into products, and that results in openness in use where there are multiple competing products that can interoperate. So far, and maybe this is because it's at such an early stage of development, quantum information technology and communication standards work, it's very fragmented and it's distributed across multiple institutions. And the ITU Quantum Study Group itself warns, I have a quote here for you. These candidate standards may overlap and conflict, preventing any single standard from being broadly adopted and forcing companies to bear the financial burden of making their products compatible with multiple standards. So that's an important issue. And the other side of that is that some of these efforts appear to be involving a resurgence of proprietary enclosure in the form of what look like standards-based patents. So that's an area that would be, any one of these would be an interesting discussion in a day-long deep dive on this. But I have a book called Opening Standards. I'm a big advocate of open standards, and I believe that they have enabled many good things about the internet, including transparency, open participation, and the ability for people to innovate. A fourth insight is that this should be obvious, but it's not always. Standardization does not mean implementation or usage. Many times throughout history, widely touted standards, this is both around digital technologies and beyond, they've not translated into product implementation or widespread usage. I'll just leave a placeholder there for Dr. Brayman to pick up on in the history of the internet. But the same thing with quantum standardization, without demonstrated workability and without coordination, it will not translate into product implementation or network implementation or usage. So that's an important caveat to remember. And finally, standardization in this space will be highly political and highly politicized. Anything involving security standards is, but especially encryption, it's always been political. It's been highly regulated. It's been sometimes banned. It has been at the center of battles between securing critical infrastructure and the digital economy versus and providing privacy versus the needs of intelligence gathering, cyber offense, law enforcement, and other kinds of values. And of course, new public policy issues will arise. What are the implications for the environment? What are the implications for the future of warfare? Many different kinds of policy concerns. So because of that, what I've tried to address today and what I'm working on in my paper is what we could call anticipatory governance. The idea that shaping public policy for the next generation requires attention to quantum standards in the contemporary moment. So it's especially for this reason that I'm honored to work on this project. I appreciate the opportunity, and I especially want to thank everyone for joining us today. And with that, I would like to turn it over to Dr. Sandra Bremen. But Sandra, before you share your slides, I hope you don't mind. I wanted for anyone interested to know and emphasize that Dr. Bremen has done a lot of extensive, groundbreaking, long-term work that looking at the public policy concerns and standards, and that anyone interested is invited to read her many articles. So thank you very much. And with that, I will stop sharing and allow Dr. Bremen to share and to suggest her recommendations and remarks. Thank you.
Okay, a screen and sound, I hope.
Yes.
Great, thank you. So thank you very much for that terrific talk, Laura. I had signed up for a classical respondent's job, but actually it was Laura who encouraged me to go a bit further and offer some more detail about how the architecture and design issues look for a classically internet-related quantum network relative to the history of internet design decision-making. I got into this because the NSF had funded me to look at the first 40 years of the design process, analyzing the internet RFCs that actually provide both a medium for top-level decision-making about internet standards, as well as a documentation of that history, and a lot of other community building things, information sharing, and the humor and so forth. What I'm going to do today is talk through this. It is an information dense slide deck, and so the slide deck will also be available along with the video. I won't be talking through all of it, but I wanted to give a kind of chronological look at the kinds of design principles that had been put forward and get you inside the head of where the IETF, a key one among the many venues in which technical standard setting for the quantum internet is going on, to get you inside of how they're thinking about it at this point. Some of that will be quite familiar to you. Some of it may look naive, but I thought it would be valuable to see from inside the internet design community's head at what to look at what you're doing. So why it matters, it came up during the recent January meeting that internet designers knew from the start that it would be commercialized. They knew it would have a wide variety of uses and users, but they now also say that if they had better understood what those uses and users would be, they would have made some different design decisions. So another theme that jumped out for me at the recent January meeting of the center group is that, of course, many people are absolutely committed to the science of the problem and aren't thinking about applications right now, and I totally get it, and that's critically important. But in order to get from here to there about a functioning network, thinking about the applications and the consequences of those applications are also going to be necessary. So I'll be focusing on the three varieties. I'm not going to be thinking about the quantum only version, which is much, much further away, but on the two possibilities of the two different kinds of possible relationships with the classical internet. So as Laura already pointed out, how close or distant it is, it's going to have to be interconnected. And my commitment for the year actually with CQN was to think about externalities. I'd point out that efforts are already underway in the internet standard setting community, which is already among the externalities of the quantum internet, quantum networking design process. Okay, I looked at the first 40 years. I'm going to focus here on some of the points that were discovered from the first decade because I'm making the chronological argument. And what I did was an inductive reading of all of the RFCs published during this period. And doing that discovered some implicit architectural design principles and conceptual frames. That was about just under 660 documents. And other people at the time were already saying these were like the constitutional documents of the internet. One was that there was a lot of interest in expanding the usage, but at the same time, there were, as frames for the frames, there was a lot of awareness that as much as they wanted new users would have new demands and they would create new problems. They expected users to be heterogeneous, but the only kinds of users they could think about were modeled on themselves. And that included even what I would call naive social science, which was computer scientists doing research on how computer scientists use the internet as an example of early use research. They did believe that user practices should be the source of design problems. There was a lot of discussion about the difference between daemon and human users. The word daemon, based on the medieval and actually ancient Greek notion of agents that are neither divine nor human, sources of agency, action. So the daemons are in the early years were computer processes or software programs. Later on, it became other network layers. That's a misstatement. And that they knew they needed to design for both, but the inclination, of course, was to design for the daemons. However, they knew that they had to take humans into account. So it's, in the early years, the conversation was relatively informal and they didn't know we'd be reading it later on. So it's somewhat revealing. There was very grudging and bemused attention to human preferences and statements like, we just can't stop humans from doing things in the network. There were two sets of design criteria. It's a socio-technical system. So we had both technical and social design criteria that came up during that first decade. One was simply sustaining the process, and this might be familiar to those of you who are working on technically on the networks now, dependent on 5-year funding at a time, as that was also the case for the early internet designers who had to keep showing enough progress to get the next round of funding. And so that became actually an important driver, a design criterion in the early years that fell off in later years. Content reliability, separate from network reliability, and compatibility going backwards and forwards. The social design criteria included network proprioception, the ability of the network to sense itself and know what was going on. Technological democracy is the concept I came up with to refer to the ability to work not only with cutting edge computation and the fastest network speeds that could broadest bandwidth that could be accomplished, but also for those with minimal processing capacity and the lowest levels of bandwidth. There was an emphasis on telepresent, distant, and distributed computing, and the goal of stimulating innovation qua innovation, just for its own sake. Some other findings from this first decade was that tension between the geopolitical and what I call the network political was already rearing its head by the early 70s. The first time they ran into it was when they started extending the network outside the US, first to Norway and then the UK. And they it hadn't dawned on anybody that actually there were telecommunications regulations and tariffs in place for all international transfers of that kind. So they just threw it out there and then got in trouble because they hadn't bothered to look ahead at the legal and regulatory environment. A very common place where we see the conflict between the two is in how to handle security breaches. The network citizen would shut down immediately. The geopolitical citizen may be asked to keep it active, so can find perpetrators. There was a very common response in the early years that the government just needs to change its laws and regulations so the network can operate as we would like. Somewhat analogous to the treatment of, oh, those humans who keep messing around and trying to use the network. It seemed to me that given where you are in your design process, that the work on coping with instability might be useful. Of course, every aspect of what they were dealing with was changing as they worked. It was kind of sweet. You wouldn't have this thought, I doubt. But then in 69, 70, the young people, largely graduate students at the time involved, thought every decision they made would have to be permanent, and they found that paralyzing. Of course, you know that is not the case at this point. So the techniques that they used with just, I won't read through the examples, you can read them, but there's definitional labor. So over and over in this history, you'll see an emphasis on the importance of reaching common terminology, common concepts, conceptual labor, network agency, appreciation of the network elements as having agency of their own. Once you put in a technology, what are the ripple effects on other technologies? Rhetorical tools, manipulations of the process. Let's just slow down. Let's give incomplete specifications and hope someone else jumps in. Personal force. John Postel was famous for saying, I'll just be the naming czar and set up the naming system. Deference to the community was really important. So the pressure on, very strong normative pressure on consensus decision-making, and the ability to live with paradox. So one of the reasons that the RFCs became so important, the request for comments series became so important, was that they felt that if they documented everything, at least they would be able to keep track of all of the complexities and ambiguities and how they found their way through them. It was also clear as you read through the RFCs that there were those active in the internet design process who were able to use ambiguity and paradox, instability and uncertainty in very canny ways to achieve the design solutions that were their preferences. Important to RFC was 1958 and 1996, that the Internet Advisory Board actually wrote with Carpenter as the editor, putting forward architectural principles of the internet, making the comment that no one had ever actually put these architectural principles into place. The ones I pointed to and others that are in the publications were implicit, were things that I could pull out with a secondary reading looking for them, but no one had just said, here are the architectural principles. So famous phrase, the evolution of the internet depends on rough consensus and running code. They took the position that connectivity is its own reward, more valuable than any application. And in fact, when they first did research on users of the internet, the number one use was being online, a similar kind of thing. The end-to-end argument was key, which meant that ideally you had to have only one protocol operating at the internet level, even though you can have multiple protocols with some differences at other levels. That protocol had to be independent of hardware medium and hardware addressing. Of course, quantum is not there yet. There was an emphasis on functions, and in fact, it was felt that certain required end-to-end functions could only be performed correctly by the end systems themselves. This document works through a number of other design, naming, and security issues. I'm not going to have, I don't have time to talk through all of them, but the emphasis on modularity was important. Performance and cost matter as well as functionality. I know that those working on quantum networks are aware of cost and performance issues as well as functionality, although the focus right now is functional. Again, the emphasis on the importance of standardizing terminology and naming procedures. The emphasis on making sure your designs are international with support for localization. And there was a preference for unpatented technology. We know how far that went, but they took the position it was okay if patented and available at all, to all at reasonable terms. And one of the things that is really, I know Vince served comments on this as something that was really very exciting to them, that there are people in the world who have built internet type networks using only this document series as their technical guide. So it was quite an accomplishment in that regard. By 2000 already, though, they were talking about the end of end-to-end, that internet developments had undermined that principle in ways that could compromise the internet's original design principles. There was fear that key features would be lost, including the ability to support new and anticipated applications. Again, it's worth highlighting that for the socio-technical system, this conclusion, this analysis was reached both by computer scientists and by legal scholars who were concerned about the policy implications. The factors that brought that about were the rise of new stakeholders, in particular internet service providers, new government interests, changing motivations of the growing user base, and a tension between the demand for trustworthy overall operation and the inability to trust the behavior of individual users, malicious users. A really important book was published, in my view, a really important book was published in 2016 by David Clark called Designing an Internet. Clark led all 5 rounds of the NSF funding for research on the future of the internet. So this book is a synthetic analysis of what all of those projects were, what the fundamental design issues were, and then he makes a stab at offering his own synthetic solution for them. As a thought exercise. But if people involved in the quantum quantum network design process were to read one book on internet design, in addition to Laura's on protocol politics, it is this book, Designing an Internet, that I would strongly recommend that you read. So he writes about architecture as a process, an outcome, and a discipline. He points out there are 2 keys to building a network architecture. One is putting things together, which is where the quantum effort is right now. But the second actually is doing so for a purpose. Again, back to that original point from the first slide that had people known how things were actually going to be used, they would have made some different design decision. So thinking ahead to applications is actually important. He warned about the second system syndrome, the tendency that after you've built a system that does a few things well, then people want to build another one that tries to do everything, rather to go forward with the first one and improve it. The things that he would argue need to be in a comprehensive architecture would be, of course, those things you have to agree upon for the system to function, things on which it's convenient to agree because it makes everyone's lives easier. The basic modularity of the system has to be agreed upon. And as I understand it, for quantum networking, there are 3 different kinds of modules that will be involved: the physical architecture, the differences in the technologies used, administrative regions, and error management schemes will also create different kinds of modules. Be aware of functional dependencies, and one of the things the RFC system does is it points to dependencies and interdependencies among different protocols, and to have a keen eye on the aspects of the system that should be viewed as and treated as long-lasting and supported in that manner. Initially, they thought the goal of the internet was to provide the service connectivity, and of course that remains the goal. But they recognize that different kinds of services may require different kinds of algorithms. They added, as they went along, quality of service, the ability to tailor parameters of delivery to requirements of particular applications, and they added storage of information along the way. Future internet options being given a lot of attention at the time the book was published, and still today, are packet delivery to a service rather than to a named receiver, and information-centric networking that is not focusing on sender-receiver addresses, but the information itself would have the label, and that's how the routing system would be, what it would be organized around. Completely different approach. Some goals of the network design system that he talks about in the book, like future-proofing, are obvious. Others have not been so obvious, and so he made a big point of stressing them. And from what I've heard so far and learned so far about quantum networking, I think it's worth stressing for you. Management was a weak aspect of the classical internet from the start. Didn't understand it that it was going to be a problem during the early years. Still don't know which management functions can be automated and which cannot or should not. and economic viability. And he talks a fair amount about some things they tried to do that with the internet that completely failed because nobody in the corporate sector was inspired to produce the things they needed so that they would be there to support those functions. Among the lessons learned, I'm looking at the time, I'm just going to put these up here. And again, the slide deck will be shared with you. So the current status in the Internet Engineering Task Force is that actually there are 2 quantum related RFCs in place, 6 drafts under discussion. These are not just in the Quantum Internet Research Group, but appearing in other of the work groups as well. The Quantum Group it meets 3 times a year and has an active listserv, about 1,000 posts at this point. I wanted to give an example of a question that came up on the listserv because it's pertinent to things CQN might think about going forward. They're asking, what is the difference, very recently, what is the difference between the quantum state and qubits? So the 2 RFCs that are published are the joke one that Laura mentioned, and here's a proposed standard that's already out there. I've just listed here the 6 draft RFCs, and you can see they're coming from different entities, the network working group and other places. The label informational or standards track is part of the genre distinctions that are made within the RFCs. So very quickly, architectural principles of the draft document, and these time out, they've got a 6-month life, is the emphasis again on applications, which again, they say seems trivial, but it's not, and point out that transmission is the building block, but not the most basic one. The importance of developing performance metrics that include fidelity, especially difficult because monitoring destroys qubits. So what kind of sampling can be done that sacrifices qubits and bell pairs for evaluation purposes? Again, the need to be future proofing, but that includes supporting heterogeneity across the physical management and error sensitivity boundaries. We're far from that as I understand it at this point yet, but for them, it's an explicit goal to incorporate varied hardware and tech support from the beginning. Security, availability. It's very interesting to think about the fact that on the quantum side, it's not connection, but entanglement. That's a fundamental service, so lots of implications from that. Fidelity is considered a part of that service. In classical networks, errors are eliminated before they get to the application. In quantum networks, applications have very different fidelity requirements. The network has to balance those kinds of things. Time is an expensive resource, and the problem of the lifetime of quantum memories, as you all know better than I, are among the most difficult issues for operating extended network. Then the second draft that is immediately pertinent to the group as a whole would be their application scenarios, excluding those specific to a node, focusing again on those associated with the classical internet. They use 2 approaches, by usage and by the distinction between planes. These are I wanted you to see the examples of applications that they're thinking about in each of the 3 categories of usage: cryptography, sensors, and computing that Laura referred to and everyone refers to. But these are the examples that they're specifically talking about right now. Quantum money, again, will relate to Bitcoin. It was very interesting, but just so you can see what's in their heads. Because they're assuming that quantum computing will be a cloud service for the next few years, their belief is that the quantum network is going to be critically important to take advantage of quantum computing. The distinction between control and data planes, the DNS system, the domain name server would be a control plane example. Email would be an example of an application or user data plane example, and category, and some applications require both. These are the areas in which they're thinking about the need for control plane applications for the quantum network, and data plane applications for the quantum network. So this is where the IETF is right now. It leads me to considerations of a few possible next steps for the Center for Quantum Networks. and other groups working in this area. One would be, but for CQN, incorporate support for participating in standard setting conversations at the IETF and other standard setting organizations in your proposal for the second round of CQN funding. Assign someone, I think you could assign someone to track the quantum conversations that are currently underway across standard setting organizations and report back, perhaps as part of retreats and or documents available on the center website. And my sense from reading through the IETF listserv on quantum is that developing a training on the physics for those involved in standard setting organizations would really help move those standard setting organizations along in the quantum domain. So thank you for listening, forgive me for going over time, and if you need me for anything, here I am.
Great, thank you both. Those were excellent presentations. We did get a few questions. So Jean Navedo asks, historically, the world's governments have been slow to govern emerging and disruptive technologies. What are governments doing now to get ahead of the threats posed by quantum computing? I imagine mostly related to the stability problems that Laura described.
Well, that's an important question. And the first thing that I would say is that governance in this area, like governance in the area of the internet, could only be described as, or it should be, multi-stakeholder, in the sense that there's a tremendous amount of power in the institutions that are involved in the coordination discussions and the design discussions. There's also, and of course, governments. But I think it's premature to start creating a regime of regulation over quantum computing because we just don't know what some of it will look like. So it's identifying the issues, raising them, creating interchange between the different institutions. And it's not only multi-stakeholder among different actors, but it's multi-institutional among the different design communities. So I think to whatever extent a government can be a facilitator among that, that's important. And also funding the different initiatives. There really has been a lot of funding of this. China is investing heavily. The United States has invested. We know what NIST is doing. The European Union has been funding. So it's not just private industry, which has invested a tremendous amount of money in this. These are the usual suspects like Google and IBM, but also new entrants, but also governments putting money behind both the innovations in quantum computing and other kinds of quantum technologies, but also in the interventions that are designed to shore up networks in case quantum computing is a threat to cryptography.
Right. Yeah, and I just add that I think the reason we even have Thrust 4 as an entire research thrust in the Center for Quantum Networks is that NSF is trying to help with the anticipatory work that we need to do. Sandra?
Yeah, if I could just add an additional dimension, there was a kind of an amusing point began in the mid-60s, by the 1980s. There's the question of who's going to regulate it. The FCC claimed by the mid-1980s that because of the word auxiliary in the Communications Act, they had the right to regulate the entire computer industry. They were simply going to forbear from doing so right now. Well, Congress and others didn't agree, and they never actively moved in that direction. But in the last couple of decades of the 20th century, around the world, there were liberalization, deregulation, privatization efforts regarding telecommunications networks. And the argument, it was very interesting in the US, the White House, the Department of Congress, the FCC, everybody took the position that they were really working towards lifting some of the regulations for telecommunications networks in order to maximize people's ability to innovate. And I think that's another dimension of where we are right now with quantum as well. Great.
And Alina Chang asked, what's your suggestion to convince policymakers of the importance of the integration of quantum computing into everyday life without going into technical detail on the inner workings of the subject? How do you educate policymakers, if I could summarize?
Well, I think that's what, as you just said yourself, that is part of what has inspired this line of collaboration and expansion of scholarship. I want to make an observation about this, though, and it's closely related to what has happened in other emerging areas like the IoT. And that's that when you look at something like the Internet of Things, where you have connected objects, not just connected computers, the internet moving from 2D to 3D, what happened in that case is that it no longer was adequate to just have information engineers and cybersecurity people working on the products. Expertise had to come from mechanical engineering in the same way as information engineering or thermodynamics or material science. And I think that strategy is something similar in this area where, to whatever extent that we can bring together different kinds of people. Now, this question about government is an important one. I think at certain levels of government, they're already there in recognizing the quantum. If anything, it may be that there's too much hype in the government in some cases. I mean, I know that's controversial to say that. It's listed in like with blockchain and other kinds of technologies where there's a tremendous amount of hype. So I think there's already interest. So the question is how to translate the real issues around the different areas of quantum and the intersections with our system of infrastructure that all of life runs on, from society to the economy to the political sphere. How do we translate the actual issues into that? So lots of opportunities there, but governments are absolutely already interested in quantum computing. I think going one level deeper and trying to disentangle quantum as one thing into its constituent parts would be a success story in the same way that many engineers and scholars have disentangled the internet into its constituent parts and breaking that down into the public policy. That would be very helpful.
Great. It is 2:00, the top of the hour here, Arizona time. I asked Laura and Sandra ahead of time if they have a few minutes to hang out beyond the 2:00 hour, and they said yes. So I'm going to keep going with questions, but we'll understand if you need to leave for another appointment, audience members. Okay, I'm going to combine two questions because they're on similar themes. So Joseph Lorenzo Hall asks, do we know if internet governance of a quantum internet will be or even can be different from what we do now? And Narayanan Rangaswamy asked essentially the same question, but about architectural decisions. So how critical are initial design decisions for the quantum internet? Context: is the current classical internet way too complicated to be amenable to any fundamental design change? What can we learn from this? So these are both questions about path dependency. Curious what your thoughts are.
I'll take the first one, and then Dr. Brayman can take the second one. Does that make sense? Yep. The first one, the answer to that depends on whether one believes that this is something hanging out there on its own that has no connection to the internet, or whether one believes that it has a dependency with classical networks and classical computing. I don't see any way that this kind of technology can advance in terms of usage without connecting to the existing internet infrastructure, even if it's just limited quantum functionality. Any kind of a quantum network would have to be interoperable with the existing network. So if you believe that, then the logical step would be to figure out how the existing internet governance multi-stakeholder model could answer governance questions about that. So I also want to say that internet governance is not static. Any more than internet architecture is static, and it evolves over time. There are certain principles that have endured over time as well, like interoperability and openness, but that too has been challenged in many ways. So it can't possibly be static, but starting with the existing multi-stakeholder model and the institutions that have expertise over the various aspects of this would be the logical way to start. Now, that model is under threat in many different ways, especially from models that are pushing from the multi-stakeholder model into cyber sovereignty, where governments have a much stronger role in policymaking than they do in other contexts. So I would say starting from the existing internet governance model and seeing how that fares rather than starting something new.
Sandra?
Yeah, I would go along with that. I think the fact that the IETF and these other standard setting bodies that have long been involved with the internet are already working on and making specific proposals for how to incorporate quantum needs and technologies into the internet is evidence they wouldn't be spending their time on it if they didn't think it was going to work with the existing internet. We want to go back to a point Laura made at the beginning, which is just because protocols are out there doesn't mean people are necessarily following them or following them as they were intended. There's a lot more variability in internet architecture around the world than is the common perception for all kinds of reasons, some national differences, some regional, some depending on particular uses. So there are all kinds, I think there's permeability in the path dependency might be a way of putting it.
Great. Okay. Katanya Kuntz asks, what do you mean by entanglement as a fundamental service?
Okay, we should ask Michael Raymer if he's still here to answer.
Well, I mean, I think part of the
I don't
idea
think I would call it. I don't
Yeah,
think
no,
I would
I
call
mean,
it
I
a
can-
service.
What that the qubits, it's the as I understand this, but really we should ask an engineer to come on, and that it's not that the quantum information itself is going through the lines the way that bits go through lines. It's that there is entanglement at a node, and that's how information is communicated. But somebody please come on and correct me.
And it's about the correlation between
that's the thing. It's
the correlation between them.
It's a fundamental, you know, it's such a strong form of correlation that two qubits that are separated in space, can provide a service based on the application, you know, depending on the application, that wouldn't be possible in classical.
Themselves,
right.
Yeah.
And that complicates the things that are in medias res, you know, the Latin term for in the middle of things, because how do you transfer between different networks? How do you deal with, you know, any errors that are introduced?
So Katanya explains some protocols don't require entanglement. That's true, but some applications will require entanglement in order to function. So I guess those are the applications for which entanglement will be fundamental.
You know, and again, I'm passing on. I'm the water bearer rather than the boundary spanner here. I'm passing on what the IETF is thinking about and what they've said.
Okay. Finally, Ibrahim Garba asks, based on one of Laura's insights, quantum networks must be interoperable with classical internet. Will mobile devices require greater processing power to access the internet, or at least to access quantum networks?
I don't think that's answerable at this point. I would say no. I would say that, you know, if anything, they may require less processing power. You know, if the network becomes more efficient and there are different kinds of services in the cloud where things are processed to a greater extent. But I don't think that's answerable at this point, although I would be very interested to know how some in the network feel about that question.
Okay. Well, we will leave it at that unless we see any engineers eager to jump in, but I don't. So thank you so much, Laura and Sandra. This was fascinating. It went beyond table setting, but it certainly did that and helped us understand what our sort of research plan, which direction our research plan ought to go in here at the Center for Quantum Networks. So thanks everyone for participating, and hope to see you soon.
Thank you so much.